So then welcome to this 7th session in parallel and distributed computing in summertime 2025. Today we have a little bit a mix of lecture and exercise. So last time, and I hope you kind of got this, we talked about, okay, we had this example of calculating pi, yeah, where we used a quarter of a circle, the area of a quarter of a circle, yeah, that is a quarter of pi times the radius. So, and by computing the surface of this area in a kind of not very mathematically efficient way, yeah, so taking this integral but just summing over the parts is not very efficient. So because it's not very efficient, we can study the purpose of parallel programming with this. So what we did is we do a very simple integration by sampling the points of this. Oops, I hate this mouse. Now it's the other way around. Of this circle function up here, so r square minus x square. So we sample this in this inner loop here, and then we split this up between different processes and then add up the entire sum. And so last week we did this with a master and slave approach. So meaning that there is one master process which we usually decide to be rung 0. So rung 0 is doing all the output, and the other rungs are the slaves. They do all the calculations, and when they have done all their calculations, they send everything to the master. And as you remember, maybe this worked very well because our problem is very small and one master has to deal with only a few slaves. So this problem is unfortunately not scalable in that way, because suppose now you have the master has many slaves, so it has to communicate with all its slaves, and then actually the master has too much work. This is the strange thing. Yeah, thinking about the old Roman Empire. So if the master had too many slaves, so then the master does all the work while the slaves are always lazy because they always wait for the master to tell them something to do. And because this doesn't work this way, even back then, yeah, they knew that they had to split up work. So the master decided for some slaves to be master of other slaves. So that the master would only talk to its main slave, and the main slave would then distribute kind of the work. Yeah. And this is, now coming to the Roman Empire again, they had this idea of divide and conquer. Yeah, so you always have to split. I mean, they had a lot of, in a sense you could say that the Roman Empire, there were countries that were slave to the Roman Empire, and of course this country also has a king, yeah, but the king was a slave to the emperor, and he had then his followers, and so everything split up more again and again. And so this allows you to handle the complexity. So now, yes, so how do you get this smaller? Is by splitting up, divide and conquer like this. So this is what we want to do today. Saying that each master, that there's always a pair, yeah? A pair between a master and a slave. And what we start up with is that we split our task in the same number of masters as we have slave, and one slave is reporting to one master. So, like if we have here 1, 2, 3, 4, 5, 6, 7, 8 tasks to do, what we will do here, in this case, the master works together with the slave, so the master does one part of the calculation himself or itself, and then the slave is reporting to that master. And then this master knows the result of these two calculations together. And then we do the same thing again, saying that now this master is becoming the slave of this master here. So we have only now half of the operations. Again, and we repeat this until we get to, so to speak, the master, the emperor, if you will. So, what is the advantage of this? See, this master here, so the only master that we have here, he has receives, so he has as many receives as he has slaves, while this master here has only as many receives as he has log slaves. Yeah, so this receiving of the master, of the outermost master, is the serial process. Yeah? It's the serial process of putting all the parts together. And this serial process grows much slower, namely only with the logarithm of n, if we do this divide and conquer. Okay, so how is this going to work? Yeah, so we have to split up our loop. So what we have to do is we have to have a local loop, a loop over being master. So this master receives once from its direct neighbor, then from its neighbor, and then it is no longer master, so it stops being a master. Yeah. So this is the loop over being a master. So now the idea of the first part of this lecture is to actually get this implemented, and now I actually hope that you somehow repeated this exercise of last week. So here we had, as a reminder, we implemented this integration of pi with the master-slave method. So there was integral and the function of f, and then there is the main We've already implemented this here, master slave wise, MPI init, blah, blah, blah. We had here the possibilities of several repetitions. This is something that we need for another example that we do later. And we compute a local integral. And now we do here the send and the receive stuff. And yes, here is the integrator function and the function to be integrated. So this here is this part here. Let me see whether I got it in the right. Okay, it's the round repetitions. We see where it opens and here it closes. Okay. So do you have this file? No, if you don't have this file, it is in. Okay, so you can take my version of this. So this is in PVR 2025 in lecture 6, and then there is main master slave, right? So please don't modify this, but copy it to your own folder. Okay. Now let me. Now this here, right? So this here is, since you don't have it, let's just briefly recap this. So what we do if my rank is 0? So my rank is 0 is obviously the master because it's the master process. So the master process has the receive buffer, and it loops over all the sources. So overall, it starts from the source 1, so this is its first slave because it itself is 0, and it loops over the number of processes. And then it does the receiving of all of them. So if we are not rank 0, we are a slave, and the slave has to do only one thing: it has to send to his master. So the slave has to do, less work than the master in this context. Okay, now this is what we had before, and this is now what we replace by, so how's this done? Control dash, yes. Okay, so this is what we now take out and try to implement something else instead. Namely the divide and conquer. So, how again is this done? Now, okay, let's go back to the lecture. So suppose, for simplicity, I have to do something before I forget this. we should rename this to divide int. Okay, I'll rename this to DC, so just that it makes more sense. Okay, how are we going to do this? So now we need to have a loop for the receivers. See, for the masters. It's an interesting thing that if you look at what is happening here, so the slave sends to the master, yeah, and once the slave has sent their information to the master, the slave is done. So sending is done only once, right? Whereas, so we don't need to loop over sending, we only need to loop over the masters in our process. So we have to have a loop for the masters, and the master then has to, of course, compute the index of its slave. So we see first the slave is just one up, yes, is the next neighbor, and then the next time it is the next neighbor, okay, and then it's again so it's not the next neighbor, but it's two more. So what actually happens is it is 1, 2, 4, 8, and so on, yeah, further away. So now we have to do this kind of calculation. Okay, let's have a look how to do this. Divides, okay, we are here. So we do the local integral, and right, we say that the result, okay, we start with, maybe I should, I don't know, I should potentially put this later here. Okay, here we do our divide and conquer. So we have the local, we do the integral and we put the local integral in our result, which previously we started with, I believe we would have set this to 0 up here, right? So now our divide and conquer. We need, okay, we're looping over the masters. Master first. So then we need to have a receive buffer. Say receive buffer where we get our result in. And yeah, now we need to loop over our receive index. Okay, I make a suggestion that we don't loop our receive or from the sending index, we loop over the distance, yeah, from our index to the neighboring index, because this would be the 1, 2, 4, and so on. So that would be simpler. So I call this now offset. I call this int offset, and we'll start this with 1. And yes, so let's first start how it will be offset equals to offset times 2, right? So this is how we increase it. So now we also need, what happens? Disconnecting, attempting to reconnect. We are disconnected. Hopefully we are now connected again. So we have to have kind of an a termination clause. So when do we terminate this loop? So termination would mean, when is the last time we are expecting to receive something? Any idea? Okay, let's say we have to, we don't want to run out of our, domain. Say, I mean, there are different ways of doing this, right? But I would say that we have to make sure that the one process that is supposed to send to us actually exists, right? So then you say that if the offset needs always to be smaller than the number of processes, minus my own rank. So this means, see, if we put this, because you could put this on the other side, yeah, offset plus my rank must be smaller or, okay, must be smaller than the number of processes, because the number of processes is the rank of the highest process minus 1 plus 1. This is why it's smaller, not smaller equal. Okay?
In the previous slide, offset was 8.
The previous slide. Okay, so yeah, so this example was 8, yeah?
Yeah, the rank is at the last
So the rank was 8. So it's the, yeah. So what was the question?
No, I mean, is it smaller?
So if you, so we increase, okay, so what's, when, suppose we are 8, right?
Oh,
So then we start with offset 1, coming up to 9. Then we go to offset 2, which is 10. Then we come to offset 4, which then is 12. And the next would then be 8, which would be 16. Yeah, but now number of processes is 16 minus 16. There's a 0, and this is smaller than my rank. So it will terminate here.
okay.
Yeah? So this is my interpretation here now. So, and in here, we have to do the receiving. So we have to do MPI receive. So the thing, so we put what we receive in our buffer into the receive buffer. Receive buffer. We expect only one datum that comes in data type MPI double. So, okay, now important is the source. The source is my rank plus the offset. That's the source. As a tag, we simply take 0, and we need the MPI communicator, which is MPI com world. And then we need a status, and because now we do not care about the status, we do MPI status ignore. No, not statuses ignore, status ignore. Okay. So, now we receive this, and after receiving this, we put the receive buffer into our result. Result accumulates the receive buffer. Receive buffer. Okay. So, now this was receiving. Now comes sending. Okay, again, let us remind us. So everybody, okay, now there's one important thing about masters and slaves. Yeah, it's also written in the Bible, you can have only one master. Yeah, so one master can have as many slaves as they want, but each slave can always have only one master. Yeah, so that's a important principle for master-slave. So each of them has to send only once. The only one that does not need to send anything is the master, so to speak, the emperor, which is here rank 0. So this is the only one that does not need to send anything. So then we simply, so all the others have to send. So what we do is we check whether we are the outermost master. So we do this only if we are not rank 0. And if we are not rank 0, what we do is MPI send. So we send our result. I mean, it's, by the way, it's also important that we first collect everything and then we send. Yeah, so this cannot be done the other way around. So we send our result. The result is one number of type MPI. No, it's double. So I mean, we want to compute pi, so that's better double. Yeah, so this here, the number, this is an int. Yeah, because it's just how many times, how big this array would be, and this, because it's not an array, it's just one. MPI double. So where do we have to send to? Okay, my rank. Okay, now we have to compute what is the rank that we send to. Now this is our challenge now. So you see, for example, if we are here in 12, we have to know that we are not sending to our next neighbor, but we are sending to 8. So how does process 12 knows that it has to send to 8? It's actually tricky. Okay, so we may take this okay, let's so now we could try to be clever and say we have so let's say we are here in the 8, yeah. Then we have basically produced an offset so far. Okay, I mean we could think this through and see that this may have some problems. Yeah. So for example, if
Is it same like rank plus offset?
yeah, you see, it's you could think about this as the same as offset. So we had here an offset of 4, and then we are running out of additional parts. So once we reach this offset of 4 of 8, then you could say, yeah, it's the same. We have an offset of 8. We have an offset of 8. Now, in order to do this, we would have to modify this loop up here. I mean, suppose you want to use this offset. Yeah? Then you have to modify this loop a little bit because of scoping. We put this int offset 1 inside the scope here, so it's out of scope here. But this is something that is easy to repair. All we need to do is we put it in the outside scope. Int offset equal to 1. Yeah. So now we put it in the outside scope. So then when this runs out of bound, we should be able to have this minus offset, and then we have to continue on here with next thing is the tag, which we sent to 0, and the MPI com world. Okay? So that could be an idea. So, and I believe the rest will do as is. So I'm going to save this. And I don't have an idea whether this works, but we'll find out. We do to PVR 2025. Then it would be Gaia. And then it would be lecture 7. So first of all, we have to look whether this compiles. MPI CPP. So how did we call it? Main minus O say pi divide and conquer. So it compiles, and now we're doing again what we are not supposed to do, namely to run it on the login nodes. MPI run. So now important thing is we had this assumption that we can split up our trees in numbers of in what is it multiple powers of 2. Powers of 2 I wanted to say. So let's take 16 then, right? 16 because this was exactly this example, and see whether DC is actually doing this. MP minus number of processes. So bad luck seems not to converge. So this didn't work. This means there is a deadlock in this. Yeah. So this is what oftentimes may happen. Now we have to find out what that deadlock actually is. So basically, a deadlock could. So the deadlock will in general be produced by the send operation, or by the not matching up these two guys here, such that some receive operation is not matched with a send operation, or that the send operation is okay. So, or that they are called in the wrong order. That could be the possibilities. So, in principle, this thing here, MPI send, so we have said that all of them, unless they are rank 0, would send once. Yeah? So then the problem could be that they are sending to the wrong offset. That would be one possibility. So this is why they don't get anywhere. By the way, we can try. We can try to run this with 2. 2 is also locked. No. Wait. Okay. 2 were. It just took longer than I was expecting. Let's see whether 4. Okay, 2 worked. 4, I would say, do not work. Okay, so the two worked. So what happens? Why did 2 work? So we start with 1. So we send. We are trying to receive from 1. And then we are sending from my rank minus 1. I think that we have to multiply this here by 2. Wait, no, I did. Okay, I believe it must be one further. Let me compile this. No. Okay, so this doesn't work. This was not.
Maybe rank plus offset.
Hmm?
My rank minus offset. My rank was 8 and offset, if we consider 8, it is 0. It will not run out.
Okay, now we can think about these numbers. Yeah. So for example, we have 4 here. Yeah, and saying that my rank is, so my rank is the last one, say it's 4, or no, so my rank, so what happens? My rank is 3, yeah? So if my rank is 3, then number of processes minus my rank.
Here, if you do it 16, that would be offset of 8. If it's offset of 8,
So here we get into our deadlock,
yeah.
right? So our challenge is now to identify how this is correct, how this is correctly done, why this doesn't match up. So let's say we are in, so which one do we want to take? One that's not, say we are 10. Yeah, we have rank 10. So what happens to rank 10?
I think in the receive buffer, we
Yeah.
have to make it my rank minus offset, and in send buffer, my rank plus offset.
So in the receive buffer, no, that's not correct, because we get our information from our right neighbor. Yeah, so we get it from the one that is higher. So we get it here from wherever is higher. I mean, one possibility for this not to work is also.
But receive should be done from a lower rank, right? Send should be done from higher rank. Am I wrong?
Yeah, so send from. So we send to a lower rank because we want to, you see, the one that worked. Yeah, so the one that worked was the one with 2. So the one, this is offset. There were only 2. That means that the second one, so the one with rank 1, he got an offset of 1, so the number of processes was 1, my rank was 1, so this is number of processes. Okay, no, the number of processes is 2 minus what my rank is 1, yeah? So this is then 1, and then then it never went through this. Okay, so then it never went, so why then gave it, okay, say again. We start with offset equal to 1. We are now process 1, so we have rank 1. We have number of processes, we have 2. Then 1, then we compare 1 is smaller than 1, which is not true, so we immediately return. Then this should also not work for 2. Why did it work for 2? Because it would send, do we have another send here or receive here? No. So this would okay, no, yes. So, right, it would, no, yes, when we are, okay, I see. When we are in 0, so this would work like this, because the 0 process has offset 1 is smaller than 2, yeah? Then my rank is 0 plus 1, so it would receive from the process 2, and the process 2 comes now here with an offset my rank minus 1, so it's not counted upwards. So this is why I said this here would have to be counted upward, but this did not work either. So, ideas. I think we need to have we need to have a different condition on this too. Yeah?
Yes.
So maybe that's not condition enough. What else do we have to look out for?
Maybe offset should be greater than the number of process, not minus rank.
Offset should be greater than the number. No,
Sorry,
that's not.
Less than.
No, because the ones.
Offset should be less than number of processes, and down my rank minus offset, then down in the send my rank plus offset.
You see, the problem is that when our rank is smaller, then
in
so this is not sufficient, yeah, because when
here what 9 is sending to 8, 10 is sending to 8, 14 is sending to 12, so the rank receiving is on the lower side.
yeah, the rank that is receiving, but the rank that is receiving, so, okay, that's an important thing. The receiver has to specify the rank of the sender.
Okay.
And the sender has to specify the rank of the receiver. Because they already know where they are sending or receiving, because they know what they are, they have to specify the other one. Now, you see, we observe this here is not sufficient because we have not made clear that we look only on, say, we have to terminate this when the offset, so when my rank, say we have another, okay, we need another condition. And this other condition is that if my rank so it has to be so my rank always has if I divide my rank by 2, sorry, no, but not by 2, by the offset, so the offset in the next stage. Then this has to be divisible. What's it called? So, you see, I have to, going back to the lecture. Okay, so if my rank is, for example, 8, then I can divide this by 1. I can divide my rank by 1. I can divide my rank by 2. And I can divide my rank by 4. And I can also divide my rank by 8. But I can no longer divide it by 16. So this is the condition that in addition we have to take care of. Let me see and save this. And let me compile this and try to run it. Okay, now you see that it runs. So we need this additional condition in order to make this here run. Okay, let me briefly go back to, so now we have the Cinder index. We also one important question is, does it work when not a power of 2? So potentially, let me see, potentially this also works when not a power of 2, because we have already included the cutoff for, I mean, we already looked whether something exists there or not on our right-hand side. So I guess let's be fancy and say we take 13 and run it, and we see it apparently does not run. Okay, so let me try this again with 8. So 8 is no problem. 32. Oh, okay, the computer has only 20 cores. No, doesn't work this way. So, but anyway, something like 12. Okay. So this is now too primitive because we simply, so the reason why this is too primitive is now, I would say, in this where we send back and do not care whether this rank actually exists. So we could try the following, adding here as an additional condition that my rank minus offset, my rank minus offset is, so this should be larger or equal, my rank minus offset, so this is where it's sent to, and it can only be sent, the smallest one could be sent to 0. Good morning. Okay, let's try out this one. So we have to compile it again. First of all, let's do it with 8. So with 8 works. With 12. Okay. It did not work with 12, so this was then apparently insufficient. So why was this insufficient? My rank, is there anything wrong with this?
The other condition should also have an extra bracket.
Hmm? You mean the receiving?
Oh, in sender end.
Send here.
My rank not equals to 0. Above this.
If here.
Yeah.
Yeah.
That condition to be separately closed. I mean, my rank should be separately closed.
I mean, you mean that there should be a bracket or what?
Yeah.
Okay, I don't think this makes it. No, that's okay. We can test this, but this doesn't make a difference. Let's That's not the same. No, we got into another deadlock now, but we have more help now, and you just came right in time to solve our problems and explain our deadlocks. Okay. Here again, so we are doing divide and conqueror. Here's the picture. Now we're actually in the case where the okay. So what we do is we split up the sending in, everybody is sending to their neighbor, then we reduce the number of processes to 1/2 of them, and they are going on to send to their neighbor until we are left to only one of these processes.
Start with 16 nodes, then
There, yes. So we would, in this case, we would start with 16 nodes. So you see, if we do this with 16 nodes now, everything works fine. Also with 8 nodes, I guess. I didn't try. It's also fine. So now the question is, we may come to the case where we don't have 16, but something else, like 10. Which means that here in this case of 10, because this number 10 does not have a neighbor, it will send at once. Now this is the idea, and apparently this here is for this purpose not sufficient. So what we do is we look at whether the offset to the neighbor is smaller than the number of processes minus my rank. Yeah, so whether this is basically saying whether a neighbor there exists, and we also see whether my rank modulo the offset times 2 actually gives 0. And then we count this up. And expect to receive from there. Now, the sender must not be 0. And the one we are expecting to receive from the one node we are supposed to send to also has to exist. you know what the problem is. The problem is that if this here terminates okay, so the problem is the following. If this loop here terminates because there is the neighbor it would receive from does not exist. Yeah, so then offset is actually not counted up to the value that is necessary for the for the opposite guy. See, the thing is the following. We would count, so for example we are 8. We are process 8. Yeah? So then we count up once 1, 2, 3, and then we become slave. And then we use this index, count it up again, and send it back 8 back. Yeah, so we count it to 4, multiply again by 2, and send it back. Now, suppose this number 12 doesn't exist as is here, so we actually have to skip over this. Yeah? So this skipping over is a problem because when we put this into a loop, it tries not to send to the process 8, to this process 0, but it tries to send it to the process 4. And the process 4 is not expecting anything. So now we have to modify. So now this is because we put this into the loop up here. So what instead we could do is taking this thing here out. I will eliminate this from here. And I'm going to take this out and say, if not this is the case, then do this. Yeah? So what does it mean? It means that it goes on counting upwards with this, even if the neighbor does not exist, but if the neighbor does not exist, it does not call the receive. Yeah, but it counts upwards so that when it arrives here, it has the right number to send back. Okay? Try this out. So first of all, does it work with 8? No, it does not work.
You have to remove the offset before.
Actually, there's an interesting thing. Actually, it worked, but it still got a fatal error. I mean, it got, no. It is. Say again.
Like in the line 64, you're already declared int offset, which I think this is redundant, but below you also have to declare it as int, I guess? Or it doesn't matter? Or no,
Yeah, so I have it because I'm using it here.
Because you need, okay.
So then it needs to be defined outside of that scope. Okay? So, Error. So there was an invalid rank.
The condition if
Wait.
the
It's the other way around. It's not yes, sorry. It's not, but it's this way. Okay. I was just confused. Even worse. Fatal and error message. Integer division by 0. Okay. Floating point exception. Floating point exception. So I divided something by. Okay, now a non-zero exit code. So we've divided something. Okay. Now I need a debugger. I don't have one here. So we divided something by 0. Okay, let me see whether this actually works with one rank. No, not even that. Okay, how on earth did I now introduce? So, okay, offset is smaller. Is it, wait. Is this annoying? My rank. So what did I do? My rank offset times 2. So if this is the same thing that we had here, and result plus equal to receive buffer. By the way, why doesn't this? Okay, I do it in a different way. So I do it in a different way. I use this offset again and do for offset equals to 1. Basically, I'm taking this thing here again. And I will just take this here out. So what I'm doing, I'm running the same loop again. I'm not doing anything, but I will have the offset that basically is after running it to that particular value as before. So let me see. whether this annoying thing now works. No. Did I introduce any new error to this? Wait. Okay, I have that's the problem with this online, lectures. You do something stupid, you don't see it, and now you have to find you somehow have to find the explanation and why it is not working. So let me see. What did I do? So this is now back to the original loop. So basically, I mean this is very strange because now we are back to the original loop. Didn't I compile it? We compile it. We run it with 8 and it should work, right? So now if I do this here again,
maybe
save it. Maybe I didn't save it, I don't know. I compile it again and I run it again. And now it crashes. Okay, so it really does not like this, even with 8.
maybe in place of my rank not equals to 0, replacing my rank modulus offset in divided by 2 condition.
Can you say this again?
Okay, the condition we have it in if my rank not equals to 0. No, the
Here,
first one.
the first one.
Yeah, not equals to 0. If we replace it by my rank modulus offset into 2 greater than or equals to offset.
What do you want? No, I mean this here. This here is here because this is the only one that doesn't send anything. Okay, so by the way, that's the only one that doesn't send anything. If it's the only one that doesn't send anything, then if it's really the only one that doesn't send anything, this should not be here. However, this doesn't matter because there is another floating point exception. Integer divided by 0. So it's the my rank of okay. There is what is what is our timing here? Okay, I am making a mess.
I believe offset must be resetting somehow to 0, because there's no other reason why it would be. Offset must be resetting to 0, because why is else coming this division by 0? I think it should come from this line 65, I guess.
Line 65.
When you're doing the modulus, I think that is the issue. That's throwing this division by 0, because offset is somehow 0, but I don't know where else could it be.
Offset is equal, how can offset be equal to 0?
But there is no other place where you're doing a division over offset.
Yeah, you know, the thing is when I have, you know, when we eliminate this line, then this doesn't happen. Did I save it? No, I didn't save it. So if we eliminate this line, then this doesn't happen. So it's
Must be that line.
no, it does not necessarily be in that line, but it is somehow implied by that line. Okay, I suggest, because we have a quarter past 11, and that there is there were supposed, okay, we'll do this part of the, this is now the first part of the exercise, because the rest of the exercise goes like this. Okay, now let's actually come a little bit to the new stuff, yeah? So all of this can be implemented in different ways, and one way that may be less prone to error is using reduce or all reduce. So reduce and all reduce uses an operation that operates over the results of many processes. So in our example, that would be that all the processes have calculated part of the integral, and now we reduce this to one number with the operation summation, so we sum everything together, and then what MPI reduce would do, it would send it to the master process. And the master process is indicated here by what we call root. This here, int root, is the master process. So it does not need to be 0, but usually, so in this picture, we would set root to 0, and then it would end up in this place here. There's also the process the function OREDUCE. So OREDUCE is different in as much as it does not only send it to one master process, but it sends the result to all of the processes, so that all the processes can go on with the same value. Now, the operations that we can specify here are, for example, maximum, minimum, sum, product, land, what is this? Logical, yes, L-end, logical end, bitwise end, logical OR, bitwise OR, XOR, and so on. Yeah, so things that we often use. I mean, all of them can be useful for different things, but what we very often have is the sum, the sum or minimum or maximum. Yeah. So, for example, you're looking for a minimum of the shortest path in a network, so you can distribute the networks over different computers, and then you would out of these you would pick the smallest, by, for example, using the minimum. Okay, so something else to do is adaptivity. That's so in order to calculate this integral, we have to specify how many points we take for this integral, right? And this is a number that we apparently have to choose somehow. And what we can do now is we can test whether this number was good. For example, by calculating a smaller integral and a larger integral, or say one with n points and one with k times n points, comparing the two, so the previous result to the new result, and say whether the change in when you refine is smaller than the tolerance, then stop, otherwise you go on refining. So this is one more possibility to do, and this should be one of the exercises. So now if you do something like this, then you have an iterative process. So what you basically do, you do the calculation, then you do the communication, and then calculation goes on, because you will have another time of communication. So this brings us directly to the process, to the concept of communication hiding. Namely, the question is whether all the processes should do the communication and then wait until they are told do more work, or whether they should already do more work, while they are waiting for something to happen. So communication hiding with blocking results. So let's say you have some work to do. And what is always important is that this work can somehow be split into parts. So this is very often the case, in particular if you have a loop. So the loop can always be cut into several parts that you execute one after the other. Say you have the problem, there is rank. So you do the different ranks have different amount of work to do for whatever reason, and they want to communicate. Say they want to communicate with all the others, so they do a broadcast. The thing with the broadcast is that it is blocking, and it returns only when all the functions have called the broadcast. So in this sense, if you use a blocking broadcast or other blocking functions, then what you would like to do is you would put this as late as possible. So do all the work before you call these things. Because if you put them early, so you get, they will all be blocked until the one that calls it last will actually make it free. So, but there isn't even, but otherwise, what you actually would like to do is to just not block it and send information that you want to send. So the idea is always, okay, why do we split up this work here? So the stuff that is being sent around is supposed to be in this first work item, right? So that this work here can be independent of broadcast, while this work here is dependent on the broadcast. So in principle, what you like to do is to send out the information that can be sent out as early as possible, so that you can go on with your work, so that you never need to wait for anything, right? This is then possible with asynchronous with asynchronous communication, with immediate, so this with IB cast, so this is immediately return. This so this returns immediately. However, it then has the problem that when you need the result, you have to somehow specify that you now need it, and for this we use wait. So in this case, we have an asynchronous communication here. Then, because the rank 2 depends on the arrival of this information, it calls a wait. Yeah, it sends as early as possible, but then it does work again, and then it waits here. To spend as little time in waiting as possible. So this sounds crazy, but the idea of waiting, of the function wait, is that you wait as little as possible by specifically stating that now you want to wait and everything else being asynchronous. So how does waiting work? So waiting requires what we call a request, because you could wait for different things, obviously. Yeah. So this always works together with this asynchronous functions like MPI send. This MPI send, in addition to what MPI send uses, it also has here a handle to a request, and this has to be defined as MPI request. Then, after you send this, you can go on working something, and this working, what the work that you do here, happens at the same time while your hardware is sending away your data. Yeah, so in the optimal case, sending data and doing work is completely overlap, such that the sending and receiving is a free operation in the end. So this is the idea. And this is why it's called communication hiding. So then there will be a time when you need the data to be received, and for this you have to call this wait. And you have to call this wait with the request in order to show what you're waiting for. And then you can do other things. So in previous years, I noticed that that this waiting and the requests led to several confusions. So this was one of the main mistakes that I found in the homework done, is with waiting in the wrong way. The thing with waiting and communication hiding is, if you don't wait, if you don't call wait and you do asynchronous communication, and it just so happens that what you do next takes up enough time for the communication to finish, then your program will work as you were expecting it. Yeah? By coincidence. Yeah? Simply because, it is somebody. So somebody delivers you. So you're at home in the kitchen and you're cutting onions, and you depend on somebody delivering onions to you. So you're always taking, you're picking them up and you are cutting them. And if they always come in, so that you always have them when you need them, then everything is fine. But one day there will be something slow with your network, yeah? Simply because something else was sent around the network at the same time. And then the network is slow and communication takes longer than you were expecting. And then you suddenly run into trouble that you did not expect. And this is one of the reasons why software is buggy. Okay, there's other reasons why software is buggy. We just generated some buggy program, obviously, yeah. But for example, there are these cases where stuff just took long enough such that you did not notice that you would have had to wait. And with waiting, you can make a lot of mistakes. So, for example, if you have a request, so you do two sends, say, two asynchronous sends, and then you think you are clever and you're recycling, what you do is you are recycling your request. You don't want to have an own request for all the different sends. So this perfectly works, and it may even be reasonable for some conditions. However, because this request is the same request as the one before, it will only wait for the last message to be sent. Because here the request was overwritten. So this will wait if this second function returns, is received last. So it only depends on this. So you get into a trouble if this here has been received while this has not been received. Very often this will not be the case, because this you send first. Yeah, so you send this first, so it makes sense to assume that that has been received first. Yeah, but there's no guarantee. In particular, if you send it to a different destination. So here you can run into trouble. So the better thing you do is you get one request for each send operation that you do, and in order for then wait, for example, for all of them, you can also use this wait all. So this wait all takes a list of these requests together with the number of requests that are in the list. So this you have to specify, because this array here is of course a pointer to an array where you explicitly have to specify how many they are contained. So then there is a few other weight statements. For example, MPI weight is the usual one. Then weight all. Then there is weight any. So this will return if any of the specified requests have terminated. Then it will also return the index of the rank of the one that first returned, yeah. And you can also wait for some. There you have to specify for how many you are going to wait for. Yeah, so for example, I could say I start my lecture if there are at least 2 students. So I've not today. You see, I'm not a wait some guy. I'm a wait any guy. Yeah. So because if anybody is here, I start the lecture. So in addition to waiting, you can also test. Test is something like an immediately return of weight. Yeah, so test is just it's non-blocking. So you can ask whether with test you can ask for a request whether this has been received. If the request operation is not complete, this flag here will go to 0. Otherwise, we'll have a non-zero here, and from this you know whether this has been received. So, for example, you can use this like here. So flag equal to 0 means it has not, or flag it has not yet been received. So you do some sending, you do some work, and then, for example, what you could do is you could say, while this flag is equal to 0, you test it, you do some work, and then you test it again, and once it has been received as non-zero, you get out of this and then you know that it has been received, and then you go out of this. So similar to waiting, there is also test all, test any, and test some. Yeah, where, for example, this test sum is a little bit different from the wait sum. So the test sum will in this out count tell you how many of the ones you are testing have now returned. Okay. Now, yes, so there would be a few things that we would now to do is implement the tolerance check with MPI bcast. Also use a job file actually, which I did not do. And then assignment 2, do the communication hiding with ebcast and wait. And assignment 3 is to use the reduce operation. Okay, so this would be, there's a few questions that you can investigate. Do the different portions gives the same result? The different ways of doing things, the same result. Smaller errors, master, slave, divide and conquer. Would you think they have different errors? No, you don't. You look skeptical.
Yeah, but eventually if you run
Okay, now,
You can iterate.
no, they divide. Okay, so this is something for you maybe to think or to try out. Yeah, divide and conquer and master and slave.
Divide and conquer has small level errors.
Okay, can you explain why?
I mean, like where in master slave, it's the only master which has to do complete things for all the slaves. Where here, if like in the program what we did it, if one thing is missing, it's still okay.
I mean, it is your explanation. You are right, but your explanation is not.
Okay.
So yes, it is the. You know, it is. The problem is not that the master does all the work. The problem is the order in which the master does the work. So, because the master, so what the master does is it is taking the first number and then it's adding the second, then it's adding the third. So, and this way of adding up numbers is different than if you have always, you know, two parts next to each other that you add together, and then you add these two parts again, yeah. So because okay, so why is this a difference? So if you have two small slices and you add them together, they are probably of similar size. So you're adding up numbers of similar size. Since they are of similar size and you're doing floating point numbers, they have the same exponent. So they will have minimal round-off error. And you do this several times because now the parts that you pile up, they become larger, but they are all always of the same size. Now what the master slave does, so the master in the first instance, it is adding two slices of the same size together. Then it takes this and takes another slice and another slice and another slice. So while it is piling up these slices, the number that the slices are all of the same size all the time, but the number they are accumulating in, this is getting larger and larger. So when you come to the end, this one number is much larger than the slice you are adding to. So the round-off error becomes larger and larger while this is accumulating. Okay, you can try this out. Actually, this is now the place where I'm stopping the recording. And I think we also deserve a break.